Okay, so now we are going to move on from discussing molecules and the individual particles to talking about how those particles interact with one another, specifically chemical reactions. So before we can talk about what happens during reactions and so on, we need to know how to read a chemical equation. So you read a chemical equation from left to right, and it's just that the things on the left are called the reactants. The reactants come together, they interact, they go boom, and they make products. Okay? Products are what you find on the right. Okay? The arrow is where the magic happens, or the chemical reaction, and you can read that as yields. So your reactants yield your products, or your reactants become your products. So, for example, here we have water reacting with carbon dioxide, yielding carbonic acid. Okay. So, just water, CO2, carbonic acid. These are your reactants, and these over here are your products. So, fairly simple, fairly easy to read. Balancing chemical reactions and the thing we call stoichiometry, that's where we do math with reactions, is going to be a little bit more challenging. You can use more symbols to specify reaction conditions. So water can react with carbon dioxide pretty much any time to make carbonic acid. But let's say you're talking about calcium carbonate or limestone. Okay. If you heat it up, you can produce calcium oxide and CO2. Okay. But it doesn't just happen by itself. You do have to apply heat. In this case, the triangle, the delta symbol, means heat. You can use other things. You can say that it takes place in water for any sort of chemical reaction. You can say that it needs, for example, sulfuric acid. You could specify some sort of catalyst. You could specify that it takes place at a specific temperature. But the things that you place above or below the arrow here, those indicate reaction conditions, what you actually need that's to have near the reactants without necessarily being reactants. Now, for this particular reaction, none of these things on the bottom are necessary. All it takes is heat. For those of you who are curious, this is limestone or lime, and this over here is known as quicklime. These were used very often as building materials because limestone is available kind of everywhere. But you take quicklime, you add water, and you can get calcium hydroxide. This would be slaked lime. And this was one of the earliest versions of concrete. So you have lime, quicklime, slaked lime. All these different things are used as building materials. And we've just described a couple of quick chemical reactions involving those things. So reading these isn't all that difficult. But balancing them is something that's going to take a little bit more practice. You'll probably have noticed that I had a little bit more information in that chemical equation. Specifically, I had this guy right here, indicating that our limestone is a solid, that it produced a solid calcium oxide or quicklime, and gaseous CO2. Physical state matters quite a bit for any chemical reaction you care to name. Just to give you a quick example, solid iron and liquid iron are going to be very, very different. You should be very, very cautious about trying to pick up liquid iron, for example. Don't ever try to pick up liquid iron. It melts at a very high temperature, something like 900 degrees Celsius. You will lose your hands. solid iron, less need to be careful with that. Okay? But physical state also matters for chemical reactions, because liquids can react more easily than solids, gases can react more easily than liquids, things like that. This last one, over here on the right, AQ, means aqueous. That means that it is dissolved in water. So we've already seen a little bit of that when we looked at acids, such that H2SO4 liquid is hydrogen sulfate, and H2SO4 aqueous, meaning dissolved in water, is sulfuric acid. That's not really a change of state so much as a change in composition, but it's something we see an awful lot. And we tend to work with aqueous solutions of stuff rather than with the pure solid or liquid, just because it's easier to manipulate and you have more control over the amounts you work with. It's a lot harder to get a very small difference in it, a difference of 1 or 2 grains of some kind of salt. Whereas if you dissolve it in liquid, then it's a lot easier to get just a milliliter to dilute things and things like that. Okay. We've already played around a little bit in the lab with some chemical equations, but do not ever change the subscripts when you're balancing chemical equations. When you're trying to balance chemical equations, you only ever change the coefficient, the number that comes in front of the substance. Never change the subscript. Okay. O with an invisible subscript. With no subscript, that's an invisible 1. We don't write the number 1. We can just assume if you're writing the atom, it's because there's an atom there. So the invisible 1 means we're looking at atomic oxygen, an absurdly reactive and toxic substance. O2 is molecular oxygen. That's the oxygen of the atmosphere. It's very reactive, actually, that it's necessary for life as we know it. Then O3, a minor component of the upper atmosphere, ozone. It's more reactive than molecular oxygen, less reactive than atomic oxygen, and it absorbs ultraviolet radiation. Those are 3 very different substances. If you mess around with the subscript, then you're talking about an entirely different thing being involved in the equation. Now, in the same way, H2 plus O2 yielding H2O, okay, gaseous hydrogen plus gaseous oxygen yielding liquid H2O, that's producing water. Okay, water is nice, safe stuff. We swim in it, we drink it, we're 75% made of it. It's very salubrious. But you change the subscript, you've got H2O2, and that's hydrogen peroxide. A highly reactive compound that is used to remove rust from metal. It's used to disinfect cuts. It's not safe for drinking, not even a little bit. Okay, so never, ever play around with subscripts. You do that, you're doing it wrong, and I will poke fun at you and fail you. So, we're only going to be changing the coefficients. When we're balancing our chemical equations, the thing to remember is the conservation of mass. Whatever you have to start with, you're going to have at the end. Going back to this, we have hydrogen, we have oxygen, and that's it. So whatever we have over here among the reactants is what we're going to have to end up with over here on the products. So this is a way of keeping track of all the atoms we're looking at. Okay, so over here on the left we have 2 atoms of hydrogen and 2 atoms of oxygen. They're each bound into a single molecule. And over here on the right we have 2 atoms of hydrogen and 1 atom of oxygen. Remember, invisible 1s. First thing we're going to have to do Whenever you write these things down on paper, go ahead and make sure you leave yourself space, by the way, so that you can write in coefficients. But the first thing we'll do is we'll double this. Okay. So we're looking at 2 molecules of water on the right now. And that 2 is going to multiply by 2 for both of our subscripts. So now we have 4 atoms of hydrogen and 2 atoms of oxygen on the right. And that means we're doing just fine for oxygen, 2 and 2, but now our hydrogen is not balanced anymore, so because we have 2 and 4. So we come over here on the left, we double the amount of hydrogen. Now we have 4 atoms of hydrogen on the left, 2 atoms of oxygen on the right, 4 of hydrogen on the right, 2 of oxygen on the right. So, just by changing those 2 coefficients, we have balanced the equation. We have the same number on the left as we have on the right. Everything we have to start with, we still have when we're done. Nothing disappears, nothing appears, there's no magic, conservation of mass. Let's do another example. Okay. Nitrogen plus hydrogen yields ammonia. Okay. Just a quick hint, for those of you who like thinking in terms of numbers and math, you'll see that nitrogen is 2, hydrogen is 2. That means that you can only ever get an even number of hydrogen atoms or nitrogen atoms here on the left. Here we have 1 and 3. You can get odd numbers. Okay. So that means that whatever coefficient we're going to use for ammonia, we're going to have to make sure it's an even number to end up with an even number of atoms. For those of you who like thinking about things in terms of numbers like that, just remember evens and odds and so on. For those of you who were completely mystified by what I just said, it is possible to just go through and just fiddle with all of the coefficients, increase, tweak a bit here and there until you end up with the right number. So we start off with 2 atoms of nitrogen, 2 atoms of hydrogen. We end up with 1 and 3. Let's go ahead and double the amount of ammonia. That gives us 2 nitrogen and 6 hydrogen, which means we triple the amount of hydrogen on the left. End up with 6 hydrogen on the left. And that has balanced that equation. That means that when this reaction occurs, 1 molecule of nitrogen combines with 3 molecules of hydrogen to produce 2 molecules of ammonia. Or, you can think of it as 1 mole of nitrogen and 3 moles of hydrogen makes 2 moles of ammonia. Molecules, moles, either one works just fine. What you cannot do, you cannot work with mass, not directly. You have to convert into moles or molecules if you want to do that sort of thing. And I think that will do it for this first lecture in the 3rd unit. We will come back for more examples and more new concepts when we return in the 2nd lecture.